Okay, welcome back everyone. In this video, we're going to continue talking about problem number 65 of chapter 22. And this was where we were looking at a charge distribution that was equal to some constant times 1 minus little r over big R when r was less than or equal to big R, and the distribution was equal to 0 outside of that. And in part C of this problem, we're asked to find the electric field when R is less than or equal to big R. So we're going to need to make use of what we calculated a short while ago for the total charge enclosed. So we mentioned how the charge enclosed would be the integral from 0 to r. But this time we're going to put in little r because we don't necessarily want to go to big R. And again, we'll do rho of r dv. And I'm not going to work through all the details of this integral. It's very similar to what I did in part 1, but what we find is that the enclosed charge is equal to 4q little r cubed over big R cubed minus 3q little r to the fourth over big R to the fourth. And one thing I can say to convince you that this could be right is that for any value of little r that we plug in terms of big R, the factors of r are going to cancel out. So the term on the left will get something in terms of q, and on the right we'll get something in terms of q as well. So now what we do is we plug this into Gauss's law. So the surface integral of E dot dA is equal to q enclosed over epsilon naught. And again, if we choose our Gaussian surface carefully, we have our charge distribution and a Gaussian sphere, so that at any point on the sphere, dA and E are going to be parallel to each other. So the dot product just turns into E times A. And one simplification that I'm making here is really there's an intermediate step of E times the integral of dA, but the integral of dA just turns into A, the area. Okay, so q enclosed over epsilon naught. And so what this means is that inside, so just as a reminder, when r is less than or equal to big R, E is equal to q enclosed, and I'm going to rewrite it, 4q r cubed over big R cubed minus 3q r to the fourth over r to the fourth divided by 4 pi r squared epsilon naught. And we have to make sure that we use little r for the area of our Gaussian surface because we're talking about this r right here. Okay, so we have some cancellation. That goes away completely. That goes to the second power. I'm just going to leave the 4 pi epsilon naught there. So the electric field is 4qr over r cubed minus 3qr squared over r to the fourth. And this is all over 4 pi epsilon naught. So this is the electric field as a function of r when we are inside of the Gaussian surface. And so you might be wondering, well, what happens at the boundary? What happens when little r equals big R? So we can plug that in, and we find that the electric field is equal to 4q over big R squared minus 3q over big R squared all over 4 pi epsilon naught, which is q over 4 pi epsilon naught big R squared. which is exactly what we expect. Q enclosed for the entire thing is going to be Q. So that's Q enclosed when R is equal to R. And of course, we're talking about a 1 over 4 pi r squared relationship. So thankfully, this makes a lot of sense. Okay, so now let's look at part D. And in part D of this problem, they want us to graph the electric field as a function of R. And we know that once we get outside of big R, that the electric field is going to reduce to Q over 4 pi epsilon naught R squared. So that's pretty easy. But when we're inside, it's a fairly complicated thing. We have to plug in our radius into this expression for the electric field. And so I've gone ahead and done that for a couple of representative little r's in terms of big R, and then the field is being written in terms of Q over pi epsilon naught R. And so what this does is it allows us to make a graph, and the first part of the graph up to little r is equal to big R is dominated by the negative 3q r squared term. So what we're looking at the beginning is kind of a piece of a parabola, and it actually starts going down a bit when you get to big R. In other words, the maximum, which we'll show a bit later on, actually occurs at 2r over 3 and has a value of 1/3 if we put this in terms of Q over 4 pi epsilon naught R squared. And then we can see that this provides a nice transition to a 1 over R squared relationship. So we know that for this function it's got to be a smooth transition. A little bit of calculus coming back. The derivative has to be present when little r is equal to big R. Okay, we can't really have a jump in the electric field, and we'll talk a little bit more about this when we get to electric potential. Okay, so we have a nice continuous curve here, and if you plug in all the values for the different r's, this is what you'll find as well. Finally, for part E, we are asked to find the maximum value. And this occurs at 2r over 3. And the reason I knew this is, well, I'd solved the problem before doing this video. And in order to maximize the electric field, we're going to have to take a derivative. As a matter of fact, we want to take the derivative of the field with respect to R. And just as a reminder, the field itself is 4q r over r cubed minus minus 3q r squared over r to the fourth, and that's all divided by 4 pi epsilon naught. So when I take the derivative of this with respect to r, dE dr is going to be 4q over r cubed minus 6qr over r to the fourth, and that's all divided by 4 pi epsilon naught. But then we remember to find a max or a min, a local extreme, I guess, we have to set the derivative to 0. So that means that basically the 4 pi epsilon naught is not a worry, and we have 4q over big R cubed is equal to 6q little r over r to the fourth. And we have some massive cancellation going on here, so we get 4 is equal to 6r over big R, and this gives us that the maximum is when little r is equal to 2/3 big R. And finally, we're asked to find the value of the electric field at this point. And I did that earlier in part D, but it turns out to be 1/3 q over pi epsilon naught r squared. So to sum up what we've done with Gauss's law, we've done some practice where the charge density is constant, and remember, for that, go back to my previous video, we just need to set up a nice ratio when we have a constant charge density, and when it's not constant, we have to do a derivative to find the amount, an integral, to find the amount of charge enclosed by our surface. So these are important things to keep in mind for when you're solving Gauss's law problems. Okay, thanks for watching, and we'll see you next time.